Okay, so we're doing Calcomatic Unit 6 multiple choice, 10 multiple choice questions. So let's get started here. First question, talking about Riemann sums. Continuous function, it wants 3 subintervals. Notice that we're already given 3 intervals here. So that's perfect already. And left Riemann sum for an approximation, right? Any Riemann sum is going to be an approximation. And this is saying from 0 to 9, right? And so we got 0 to 9 right here. And so it's saying left Riemann sum. Well, we already have our 3 intervals. We're going to use this one. The left is a 3. The left digit here is a 4. The left height is a 10. So if we're going from the left, right, we're using the height on the left. Like I said, left height's 3, left height on this interval is 4, left height on this interval is 10. And we, of course, have our bases as well. This is a base of 3, this is a base of 2, this is a base of 4. And what is the area of a rectangle? Area, we're adding rectangles here, right? That's what Riemann sums are. So it's base times height. So if we're going to add 3 rectangles, okay, and we're starting from the left height, so the first rectangle goes from 0 to 3. So we have a base of 3 times the left height, which is 3. Then we go to the next one. The base goes from 3 to 5. So we have a base of 2. Multiply that by the left height, which is 4. And then we add the last rectangle, which the base goes from 5 to 9. So it has a base of 4. And then multiply the left height, which is 10. So I'll just do this for clarity. And here, so we get simple 9 plus 8 plus 40. And then we get 17 plus 4, equals 17 plus 40. So we get 57. And that's our answer. Okay, so let's go to the next one. Okay, so we have I, which is the exact area under the curve. We have L, which is a left approximation, and R, which is the right approximation. Okay, and so if you take a look at the answers here, it's actually asking which is greater than which. And so we can do this. So we know that I right here is the exact approximation. So we're going to get the exact approximation with I. But let's take a look at L. So L, we're going to get basically a non-existent rectangle here. Just imagine this has a width of 0. And we just keep on making rectangles. This is just an example. So you should notice that we're missing a lot of space with L. L left approximation Riemann sums. And that's because this function's increasing. And so when you have an increasing function with left Riemann sum, well, what happens is because you're using a lower value, because the function's increasing, you're using the left height value, you're going to get a lot of oops, you're going to get a lot of undercounting. So left Riemann sum is going to be less than the exact area because you're going to get a lot of undercounting. Right? You see all this space here that's not being counted. It's an under approximation. But let's try right Riemann sum. So we do that. It's an increasing function when we're starting from the right, so you might already guess that we're going to get an over approximation because we're starting from the right instead. I'm doing my best to make rectangles. I'm not an artiste. But you can already see there's a lot of over approximation because we're using the right value. You can see all this, I guess I'll use green instead. All this over approximation. So we know that right is going to be greater than the exact area, and exact area is going to be greater than L for an increasing function. And this is true for all strictly increasing functions. So we're going to get L is less than I, right, the exact, and the I is less than R, because R is an over approximation, L is an under approximation. So, and that's why we get this. Okay, on to the next one. All right, this one's a hard one. So, this is when we're first learning about how we come up with an integral. Let's see if I can get the exact. Okay, that should be good. So, this is when we're first learning how to come up with an integral, and it's really adding up a bunch of rectangles, right? We have some curve, and we're adding up a bunch of smaller and smaller rectangles to get the area under the curve. And the way we make these increasingly small is by setting the number of rectangles equal to infinity, with the width of each rectangle going to 1 over infinity, or increasingly small, right? And we already went over area of a rectangle, base times height. Now, let's just go over a couple things. The base, when you do an exact integral, the base of the rectangle becomes infinitely small as the rectangle goes, number of rectangles go to infinity. So that's what this dx represents. And then this represents the height at each individual point. So this is your height here, and this is your base. So let's figure this out, okay? We know that we have to go from -3 to 2. So if we have to go from -3 to 2, well, then our total base, where our total distance we're measuring from, is going to be 5, because 2 minus -3, that's double negative, so it's just going to be a positive, it's going to become a positive, is equal to 5. So what does that mean for the number of rectangles? Well, if we need n rectangles to equal to 5, a total distance of 5? Well, then the width of each rectangle is going to have to equal 5 over n. So because of this is going to be the width of each rectangle. That way, when you have n rectangles, it's going to be equal to 5, the total. So we already have our base. Our base is going to equal to 5 over n. That's going to be our base, right? And so we've already figured out, well, it's not going to be C, D, or E. Okay, now we need to figure out our height. Okay, so let me just erase this real quick. Remember, all of these, you're counting for each k. So our height is represented by 1 minus x squared. That's going to be our height. So we need to figure out what we replace for x. So it's going to be something like 1 minus, just how we replace dx, because that's also an x, we're going to have to figure out what to put in for x. 1 minus something squared. Now we are starting from -3, right? And if we have to add up rectangles between -3 and 2, we're going left to right, right? So we're going to have 1 minus, it has to start from -3, okay? And so for each x, right, we're adding up all the values between -3 and 2, right? So this means, we're starting from the very lowest, k, and we're going in intervals of 5 over n. This is a very difficult problem. If we're adding up extremely small, remember this value of k goes all the way up to the value of n based on the summation. But each of these individual rectangles, if you have, you're starting at -3, and you're starting from k equals 1 to over a very large number, so almost 0. And then as this value of k increases, you're going to move further and further along as the value of k increases. But each rectangle has a width, and that width is 5 over n. So you have to move over 5 over n distance, and that's why the k is being multiplied by the 5 over n. So the final answer is this height, right? This is the height here, multiplied by the base, which is 5 over n. This is a very difficult one. Don't blame me for missing this one. But this is why our answer is A here. Okay, so on to the next one. Actually curious how they explain this. Yep, just as I had explained, they found the width first. The base is going to be 5 over n. And the starting point is going to be A is equal to -3. And so they just added that delta x, which is the base for each k. And so that's how they can plug that into this equation here. Okay. So this one, we have, this one's gonna be a little tricky. This is just a fundamental theorem of calculus problem. E to the 2t. Okay, it wants to find h prime of x. which h prime of x is just going to be the derivative Okay, well, you can already see derivative is going to just cancel out this integral, but when it comes to these problems, you have to understand, oh, there's bounds, so it's not going to be quite the same. Because of this, if you're imagine, luckily e to the 2t, you can actually integrate yourself, but a lot of times the answer they give you is going to be a really difficult integral that you don't want to have to deal with. So I'm not going to do it in terms of that. So you can say, okay, derivative, integral are opposites, so they can kind of cancel each other out. But it's not quite right to say that. They do get rid of each other, but you have to realize that when you integrate, right, you're going to integrate this function where you're going to get an x squared being plugged in. So how do I want to write this? Okay, I keep on writing in red and I'm needing to write in green. My apologies. So when you integrate this, you're going to get some function where you're going to plug in. I'll call this h of x, except you're plugging in x squared. Okay? And then, so minus, actually, it's not quite right to write that. I'm just going to call this big F. I'll call this big F to represent that this is the integral that we've already taken. Okay. And actually, I'm going to call this big H. Makes more sense to do that. These are hard problems, so don't stress too much over it. Because we're putting our bounds in, right, x squared and 0, if you take the derivative of h of 0, well, if you plug in 0 to the variable, this is just going to be a constant. The derivative of a constant is just 0. So h of 0 kind of disappears. But you are putting in the derivative of this function is just going to be this again, because we took the integral of it and we're just taking the derivative back. But it is, so you are going to get e to the 2. My apologies. You're going to get e to the 2, but instead of t, you're plugging in x squared instead of t. And so because of that, you also have to take the derivative of the inside of x squared, and that is 2x. So you get a final answer of 2x e to 2x squared. And that's the answer to this problem. Now, if you just take a look at this, like the only thing, if you have this in the future, I kind of explained why this happens, but if you just take a look at this problem in the future, you have an integral and then you have to take the derivative, just think of it like this. You have to, the steps here, you could use the derivative to get rid of the integral and keep this the same, but you have to plug in your bounds into here, so you get e to the 2 times your bounds, which is the x squared. And the only thing you have to remember beyond that is just to multiply it by the inside, which, because of chain rule. So the derivative of x squared is 2x. So you don't have to make this problem more complicated than it needs to. It's a bit difficult to explain, but we'll move on to the next problem. Yeah, so they just basically give you the definition of this. I was trying to explain more of why it works that way. The whole point is this 0. If you plug in a 0 to a function for every variable, well, then the variable, there's no more variables. So when you take the derivative of, you just get a constant. Well, you have a constant because you plugged in that 0 for every variable. So taking the derivative of a constant gets you 0. So, okay. So okay. So we're given 5 line segments. So we can actually break this up into exact areas we can calculate. And we can calculate these areas using formulas for rectangles, triangles, and trapezoids. But let's see what they actually want. Okay, closed interval, 5 line segments. Let's h be the function defined by. Okay, so they want value of h of 9. Okay, well, let's plug in this h of x. And so the h of 9, well, they want you to plug in 9 for x. Okay, well, this is pretty simple. The x is right here. So you just go 9 to 5, or 5 to 9. Okay, so it's saying 5 to 9. So we just have to calculate the area from 5 to 9. And if we add up these two areas, we will get 5 to 9, and we'll have h of 9. So what is the green area? Well, the green area has a base of 2. It's a rectangle, right? So it's base times height. Base of 2 and a height of 6 here. Right, it's right there. So 2 times 6 is 12. That's the area of the green area. For the red area, well, it has a base of 2, so it goes from 7 to 9, also a height of 6, but it's a triangle, not a rectangle, so it's 1/2 base times height. So it still has a base of 2 and it has a height of 6. And so 1/2 times 2 is 1, so you just get an area of 6. And so the total area is equal to 12 plus 6, which is 18. Right, so that's going to be the area under the curve from 5 to 9 is going to be 18. So that's how you get the answer D. Okay, halfway there. I don't know how long this video is so far, but hopefully I had a couple of hard questions. Okay. Luckily, they're giving you U this time, so you don't have to figure out U here. So let's, if we're using U substitution, we not only have to find U, we have to find du as well. So du is going to be the derivative of x over 4, which is just 1/4. Dx, remember, you're taking the derivative, you're going to get, always have to include that dx. So this means that if you multiply 4 to both sides, you get 4 du is equal to dx. And by the same token, 4u is equal to x. So we have 1 over x squared plus 16 dx. So when we plug in our u values get 1 over, well, x is equal to 4u, so we get 4u squared plus 16. And dx is equal to 4 du. Okay, so we have to simplify it. I noticed that there's only 4's in this, so the 16 has to go away somehow based on the multiple choice. Well, 4u squared is going to be 16u squared. You can actually take this 4 out to the front. And so, remember, this 4 went out to the very front because it's a constant. Okay, I don't see any 16s. I can take a 1/16 out of this entire thing. 4 times 1/16. And I took the 16 out, so I get u squared plus 1 on the bottom. And then, well, 4 is the same thing as 16 over 4. So 16 over 4 divided by 16, well, that's just going to be equal to 1/4. And so you get the answer of A right here. Okay. Notice you don't have to actually solve the integral. Make sure you take a look at the answers first so you know what to look for. You might have started solving this and said, oh, this is arctangent. You don't have to do all that for this one. Okay. Whew. Okay, this one we're gonna have to do u substitution. I mean, I don't know about you, but I don't know the exact integral of sine to the 4th times cosine. So when I have a complicated integral like this, I'm thinking to myself, oh, you know what? Probably gonna have to make this integral simpler. U substitution is one of those ways. I notice I have a sine to the 4th. Whenever I see a parentheses, and you might not see it, but you get sine x, right? Sine to the 4th x, well, you can just make it sine x to the 4th, right? Sine 4x here is the same thing as sine of x to the 4th power, still multiplied by cosine. And now that you have a parentheses there, you might think to yourself, okay, I could make sine x u to just get a simple u to the 4th, and we can try that, right? U substitution is all about guessing and checking. Let's see if this works. Let's make u sine of x. Well, du, taking the derivative of sine of x is equal to cosine of x. Dx. Okay, let's test it out. Okay, I can bring this 2 out to the front. And, well, sine of x is in the parentheses, so I'm just going to put a u. And it's being multiplied by cosine of x dx, which is this. So I can just put a du. Well, looks like we got rid of all of our x's, and we just have a simple u to the 4th. So it looks like our u substitution worked. But if it didn't, we could try something else, right? we could have tried u is equal to cosine, would have got du is equal to negative sine, but then we would have found that our du was inside of a fourth power, which wouldn't have been good. But we can take the integral of this. The integral of u to the fourth is u to the fifth over 5. But that's not all. Remember, this is undefined integral, so it's going to be plus c. So you get 2/5 u to the fifth plus c, and you can plug in back in for u. So 2/5. U is sine of x to the fifth power plus c. And that's how we get b here. Ooh, okay. This one, if I see an expression like this, a complex polynomial, well, not technically complex, but hard to solve, and I see an x minus 3 or an x minus 1, x plus 1, one of those type of things at the bottom, I might try and make this easier by trying to divide the two, trying to cancel some terms out. So let's see what we can do here. So let's try dividing this. Use some long division. X to the fourth minus x cubed minus 7x squared plus 6x minus 9. It's so long that my long division wasn't long enough. And we have an x minus 3 on the outside dividing this long function. Okay, so how do I make an x and x to the fourth? Well, x times x cubed gets x to the fourth, right? So we multiply x cubed to this function, we get x cubed times x is x to the fourth, which if it's not x to the fourth, if this doesn't cancel out, we did it wrong. And x cubed times minus 3 is minus 3x cubed. So we're subtracting this now. We're doing long division. So x to the fourth minus x to the fourth is 0. And if it's not, you did something wrong. You need to change this up here because this needs to multiply together with this to cancel out the first term. Negative x to the third minus negative 3 x cubed, well, this is actually going to turn into a positive 3x cubed. So minus x, because it's a minus negative 3x cubed. So negative x cubed plus 3x cubed is going to be a positive 2x cubed. And then, or x to the third. And so we're going to drop this 7x squared down below. And so how do we get x to equal to this one now? 2x cubed. Okay, well, I would need to, it's a positive, so x to become 2x cubed, we're going to need 2x squared. And again, x times 2x squared, it should be 2x cubed. If not, you did something wrong. 2x cubed minus 3, or times 2x cubed times negative 3 is going to be minus 6x cubed, or 6x squared. 2x squared times negative 3 is going to be negative 6x squared, and we're going to subtract this. Again, this should cancel here. Negative 7x squared minus negative 6x squared. Well, this is going to be it's a minus negative 6x squared, so it's going to be a positive 6x squared. So negative 7x squared plus 6x squared is just going to be minus x squared. And then we're going to drop this term down. So we're going to get the plus 6x down here. How do we make an x a minus x squared? Well, we just multiply it by minus x. And we're going to get that negative x squared. Negative x times negative 3 is going to be a positive 3x. And then we're going to subtract this. This is going to be 0 again. 6x minus 3x is just going to be 3x. We're going to bring down our last term, which is going to be 9. How do we get x to equal to 3x? Well, you just multiply x times positive 3 to get that will get your 3x. 3 times negative 3 is 9. And perfect. We actually get a remainder of 0, which means this divides into everything perfectly. So, in other words, because we divided this, this is actually equal to, we divide the x minus 3 perfectly into here. This is actually equal to this, just this. So we just get the integral of x to the third plus 2x squared minus x plus 3 dx. Now this is much easier to do an integral for. Integral of x to the third is x to the fourth over 4 plus 2 times x cubed over 3. Again, we're just using power rule. Minus x squared over 2. Integral of x is just x squared over 2. Plus 3x plus c. My apologies about. And so this is our answer. This is how we get c as the answer for, right? X to the fourth over 4 is the same thing as 1/4 times x to the fourth. And so that's our answer for this one. That was a long one. Ooh, it's got some big numbers here. This one's calculator allowed. So we got f of x equals x to the third power on the interval 0 to 9. Well, and they want right Riemann sum for this using 3 intervals of equal length. Let's just make a graph. Boom. Boom. Now let's just call this 9 here. And we want 3, 0 to 9, right? So we want 3 intervals of equal length. Well, 9 divided by 3 is just 3, so we get an interval from 0 to 3, 3 to 6, and 6 to 9. Those are 3 intervals. Okay. It's asking for the exact sum, so let's do that. Okay. So our base for all of them is just 3. That's not too bad. But let's start, because we're doing right Riemann sum. Well, you can start from either left or to right. I'll do the first one. I'll do the left one first. So we have to remember this is x cubed. So the first rectangle has, remember, this is base times height, right? Area of each rectangle. So the first one, base is 3. The base is 3 for every single one. The height, well, it's a right Riemann sum. So for the very first one, the right is going to be 3. to the third power, right? Because it's x to the third. The second one, again, the base is going to be 3, and the right height is going to be the 6. For the second interval, the height on the right is the 6, so, and because the function is 6 to the third, or x to the third, it's going to be 6 to the third when you plug in the 6. And then the very last one, the very last height is going to be 9. So it's going to be 9 to the third. There we go. And so when you plug in these values, you get 3. Well, 3 to the third is 27. Plus 6 to the third is 216. Don't ask me how I know that. And then 3 times, well, 9 to the third is 729. Okay, so 3 times 27, that's 81. Plus 3 times 216, that's going to be 648. 3 times 729 will be 2100 plus 3 times 29, which is 87. So it'd be 2187. And then when you add all those together, you get 2916. So our right Riemann sum is going to be 2916. So already the first 3 answers are wrong. You can figure that out. But just to go over this again, let me use blue here. We already knew that the height of our first rectangle is going to be the height of x when x equals 3, or the height of f of x when x equals 3, and we figured out f of 3 is just going to be 3 cubed. And then you do the same thing with each other rectangle. That's an awful rectangle. The height of the second rectangle is going to be 6 cubed, because you're going from the right, and the height of the third rectangle is going to be 9 cubed. Okay. Now, just from drawing these rectangles, it's a strictly increasing function. We know this, x cubed pretty much increases across the entire function. It technically has a slope of 0 at x equals 0, but everywhere else increases. And because we're doing a right Riemann sum of a strictly increasing function, you're going to get a lot of over approximation. But you don't have to memorize these rules. You can always just write these out and it becomes a lot easier. So this is why you get 2916, and it's an overestimate. Yeah, so it's an overestimate of the exact value. Okay, I believe this is the last one. Okay. We're going to be doing another one of these. We kind of did one already. It's a bit more complicated. Okay. We have h of x is equal to integral of 2x, or integral of 1 to 2x, from 1 to 2x of the square root of t squared plus 2t dt. But we want the derivative of this. So we're taking the derivative of an integral with bounds. So again, we're going to use the fundamental theorem of calculus. We're going to take the derivative first before plugging in 3. We always want to take the derivative first before plugging in 3, before plugging in the x value. So now, take the derivative of this entire thing from 1 to 2x. Okay. And so when you take the derivative, right, normally you'd take this integral, you'd plug in your 2x, and then you subtract the value when you put in 1. But when you take the derivative of something where you've already plugged in 1 for every variable, well, taking that derivative, it's going to become a constant by plugging in 1 to every variable. So when you take the derivative of a constant, you just get 0. So we only have to focus on putting in that 2x, right? Plug in the 1 for all the t values means you'll get a constant, and then we take the derivative of that constant, you'll get 0. So we just have to put in, because the derivative and the integral cancel out in a way, just by fundamental theorem of calculus, we just have to put in 2x for every t squared, for every t value, right? Because we're just going the opposite way after we plugged in 2x already. So we get 2x, and you can just memorize the rule if you want. I'm trying to give a more logical explanation for it. So I'm plugging in 2x for t, so t squared, so I'm going to get 2x squared plus 2t, so I'm going to plug in that 2x here. And this is still h prime of x. But because we were plugging in 2x and now we're taking a derivative with everything having a 2x in it, we also have to take the derivative of the inside. So the derivative of 2x is just 2. Actually, I'll do this more properly. We have to take the derivative of the inside. And the derivative of the inside is 2x. Or the inside is 2x. So when we simplify this down, two x all squared is going to be 4x squared, plus 2 times 2x, which is just going to be 4x. The derivative of 2x is just going to be 2. So it's just going to be multiplied by 2. So now we can plug in for 3. We can plug in 3 for x, because it wants h prime of 3. We can bring this 2 to the front. We plug in 3 for x. And so h prime of 3, we get 2. 3 squared is 9 times 4 is 36. 4 times 3 is 12. You get 2 times square root of 48. But we can do a bit better than this. 48 is the same thing as, so square root of 48 is the same thing as square root of 16 times square root of 3. 16 times 3 is 48, so we can break this up into 16 and 3. And the square root of 16 is 4, so we get 2 times 4 times square root of 3. And so we get 8 square root of 3 as our answer. And that's how you get our answer right here. That was an awful circle, but so that's all 10 problems. So I hope this wasn't too long. But I'll see you guys later.